Actually, I'm going to start with a poll, and I'm going to ask you, which ones do you think are decidable here? So these are, you've seen a variation of these problems, right? So these are with respect to Turing machines, but previously we saw these with respect to DFAs. Similar kinds of problems, like accepts TM is, whether when you're given a Turing machine M and some input X, you want to know, does M of X accept or not? Now, I don't want you to, like, in your mind, try to prove whether these are decidable or not. I'm just asking, at an intuitive level, what do you think? Do you think, like, the strategies that we used for DFAs, would that work in this context of Turing machines? So think about those things, and intuitively, let me know what you think. Do you think these problems are decidable or not? And just to give you, as you're thinking about that, just to give you some motivation and just to understand what these problems mean, let's take, for example, not equality Turing machines. So here you're given the description of two Turing machines, M1, M2 as input, and you want to know whether L of M1 is equal to L of M2 or not. So whenever I say Turing machine, like in your mind, you can imagine that I have some Python function that I'm interested in. A Turing machine is just a low-level description of a Python function. And suppose like you're interested in writing an autograder program that tests whether the student submission for, let's say, some Python function like is prime is actually a correct submission or not. And you have the correct version that you have written as the instructor, let's say. And I want to write a program now that will take as input these two Python functions as texts, and then tell me, like, oh, yeah, these two Python functions return true on the same inputs. Or maybe not, right? So that's the question here. So is there an algorithm that solves not equality? Accepts TM is another one, right? So is there, now you're given some Python function and some input, let's say 251, that's supposed to be fed into is prime. And I want to know, does this Python function on input 251 return true or not? I want to write an algorithm for that. Of course, when you want to write an algorithm for these kinds of things, no matter what the input is, it should give you the correct answer, right? So that's what it means to have an algorithm for a problem. So, okay, once again, these are the problems. Now, from now on, I won't use the subscript TM anymore. If I don't use the subscript TM, just assume that the machines are Turing machines. Okay, so a lot of you think, 56, like more than half of you think accepts is decidable. About half think self-accepts is decidable. Only 16% think halts is decidable. So I'm assuming that you've somehow heard that the halting problem is undecidable. That's good. About half of you think sat TM, and half of you think not equal TM. And only 20% think none of the above. So good news and bad news. So bad news is that your intuition is very off. Good news is that we're going to fix your intuition in this lecture. Okay? But before we do that, let's think, let's take a couple of these examples. Accepts. Let's say we're trying to decide accepts. What's the one natural way to go about it? When it was a DFA, what did we do? Accepts DFA. How did we decide accepts DFA? Can anyone remind me? Yeah. We just simulated the DFA on the string X, and we saw, does it accept or not? Good. So does this work with Turing machines?
The Turing machine might not halt.
Right. The Turing machine, the problem is that the Turing machine may not halt. So you can start simulating M on X, and it's simulating and simulating, but maybe it's not going to halt, right? So what do you do? When do you stop the simulation and declare an answer? Maybe you run it for 1 day, and then you're like, oh, it's still going on after 1 day, so let me stop now. But maybe you were not patient enough, and maybe after 2 days it was going to actually accept. Or maybe you ran it for a week, but maybe you were not patient enough. Maybe in 2 weeks it was going to accept, right? So you don't know when you should stop your simulation. So this idea with DFA does not work. How about, let's take SAT. With SAT DFA, how did we do that? How did we solve that one? Who can remind me very quickly? How do we know whether a DFA accepts some string or not? Yeah.
We did a graph search from the starting
Yeah, we looked at the state diagram. That's a directed graph. And we want to know, is there a directed path from the starting state to one of the accepting states? If there's some path from the starting state to one of the accepting states, then if I look at the transitions along that path and the symbols there, then if I were to read that word that would take those transitions, then I would accept. That string would be accepted. Does this work for Turing machines? Can I do the same thing for Turing machines? Can I take the state diagram of a Turing machine and say, oh, let me check, is there a path from the starting state to the accepting state? So just because there's a path in the Turing machine from a starting state to an accepting state does not mean that you would ever take that path in your computation, right? And you can construct examples of this. Like, let me give you one example. Suppose that you have the input alphabet, let's say 0, 1, and then you have another tape alphabet which also contains the character hashtag for like crossing out symbols. Now, there could be, like, let's say, a path from the starting state to the accepting state that only uses hashtags, reads hashtags, and then takes you to a starting state. But perhaps the Turing machine never writes hashtag on the tape. If it never writes hashtag, it has no opportunity to read hashtag symbols. So it would never, even though there is a path with hashtags, it doesn't take that path. It cannot take that path. So really, whether a Turing machine is going to take a particular path or not depends on the logic of the Turing machine. And you may not know with DFAs, but that's not the case. OK, good. So those things don't work. Now, this does not mean that these problems are not decidable. There could be some other algorithm, some clever algorithm that works. At this point, we don't know whether these are decidable or not, but we're going to figure out. OK? Good. So now, with that out of the way, let me now remind you the important thing that we did on Tuesday that we're going to be using today. And that's going to be diagonalization. OK? So I'm going to quickly remind you what we did. So in diagonalization, here's the setting, right? So we are given some set of functions, curly f. Each has this kind of signature. It has the input space x, and the output is 0, 1. And I'm going to visualize now these functions with a table. OK, so my functions are here listed. Let's say we have 4 functions, f1, f2, f3, f4. And the possible inputs are, let's note them by x1, x2, x3, x4. So there are 4 possible inputs, let's say. And I have this table, and it's like the truth table for each function is a row here. f1 on input x1 gives the output 0. f1 on input x2 gives the output 0. f1 on input x3 gives the output 1, and so on, right? So this is the way I fill out the table. And our goal here is to construct a function f sub d, again from x to 0, 1, which is not in this collection of functions that I'm given in curly f. Okay, so I want to construct f sub d, which is different from f1, f2, f3, and f4. Okay? And as we said, how did we do this? You can think of this as a mechanical process, if you will, in your mind. First, I'm going to make sure that f sub d, the diagonal function, is different from f1. And then I'm going to make sure it's different from f2 and f3 and so on. To make a function different from another function, all I need to do is make them different on some input. So to make fd different from f1, I'm going to choose some input. Might as well choose x1. See what f1 gives as output on input x1. And I'm going to do the opposite for f sub d. This was a 0. I'm going to make it a 1. So now I've made sure that fd is different from f1. And I'm going to repeat now. I'm going to make sure that fd is different from f2. And for this now, I will need to pick a second input, right? So now I'm going to pick x2 and make sure that fd is different from f2 on input x2. This is a 1, so I'm going to make it a 0. It is important here that I don't pick the same input, right? So if I were to say, oh, for fd, I made it different from f1 on input x1, and I'll try to make fd also different from f2 on input x1, I can't do that. Like, there will be a conflict. This is 0, this is 1. I could not make fd different from both f1 and f2 on input x1. I need to pick a new input and do this. Good. So then I move on. For f3, this is a 0, so I make this a 1. And for f4, I'll choose x4, and so on, right? So once again, how we're doing this, for every function in curly f, I'm picking a unique input x and making sure that f sub d is different from f on that input x. Okay? And what is the condition that I need to be able to do this? What is the condition needed so that I can pick a unique input x for each function that I have. For each function, I need to be able to pick a unique x, and what's the condition I need? Someone was not spoken, yeah?
You need to have at least as many x's as you.
Yes, you need at least as many x's as functions, right? So the size of x should be at least as large as curly f, so that, then, in that case, for each function I have, I can pick a unique x. Okay, so this is the lemma that we have now, diagonalization lemma. We can write it out. Let x be any set, and let f be any set of functions from x to 0, 1. Then, if it is the case that the size of x is at least as large as the size of curly f, number of functions, the number of inputs is at least as large as the number of functions, then we can construct this diagonal element, f sub d, which is not in curly f. Okay? And the crucial thing is, this is the condition we need. And the crucial thing is, this works. The previous example was with finite number of functions and with finite number of inputs. This idea works for any set x and any curly f. As long as the input size is at least as large as the curly f, this works. Right? So in general, though, of course, when x and curly f are infinite sets, I cannot really talk about the number of elements in these sets. What this means is that there's an injection from curly f, the set of functions, to the input space x. Let me denote that injection by phi. So there's an injection phi, which tells me, for a given function f, the unique x that I can pick, in the input space x. Right? And once again, let me draw the table here, right? So you could have now infinite number of functions. So let me list them out, f1, f2, f3, f4, and so on. And now I want to construct f sub d, which is different from each one of these. And now to do that, for f1, I'm going to pick a particular input and make f1 different from ft, or make ft different from f1 on that particular input. What's the input that I'm going to use? The injection is going to tell me. The injection maps f to a particular input x sub f. So I'm going to use that phi of f1 for that. So I'm going to put that as a column here. And then for f2, it's going to be phi of f2. For f3, it's going to be phi of f3, and so on. And then I can fill the table now with zeros and ones, depending on the values that these functions take on these particular inputs. And then we do the same thing. We go through the diagonal, and then we swap the values. Flip the values. Okay, so this is it. Now, when the number of, or I should say, the cardinality of curly f and curly x, let's say, are finite, or it's countably infinite, I can draw a table. I can visualize this diagonalization with a nice table like this. But I want to highlight the fact that, this lemma works even when x is uncountable and curly f is uncountable. Okay, and if they're uncountable, then I would not be able to really visualize it as a table. I cannot list them out. You cannot list out an uncountable set. But nevertheless, we're going to use it in the context of either finite or countable sets, so you can visualize it nicely in the table. But diagonalization is not dependent or equivalent to the creation of a table. Okay, it's a more general technique.
Does this work when there's a bijection between both?
Yes, so there could be, in most cases, there's going to be a bijection between x and f, and that would work, yes. Absolutely, good question. Good, so now this is diagonalization. And we observed actually a very nice corollary of this, a very immediate corollary. And I'm going to come to that. But let me just say a few remarks. This is called diagonalization against curly f, okay, the set of functions. Diagonalization crucially produces an explicit f sub d outside of f. Once you specify for me what the injection phi is, it gives you basically an explicit function f sub d outside of f. You can pretty much view anything as a function. So the reason I presented diagonalization using a set of functions is because functions are very versatile. Pretty much like sets are functions, numbers can be viewed as functions, anything can be viewed as functions. So that's why I use functions here. And the other observation is that the range, I use 0, 1 here, but I hope you see that that doesn't have to be the case, 0, 1. what can I do instead? Like in general, what can I say? The range should be what in order to carry out the diagonalization? There's really one edge case that I need to avoid, or two edge cases. Yeah, you don't want like a single element, because if there's just one output, then I cannot flip the output. So you just want any set in the range that has more than at least two elements. Okay, so I'm going to change, I change the lemma now. So to make it a bit more general, f maps x to y, where the size of y is at least 2. When you have this, then you can go ahead and diagonalize, no problem. Okay. And now let me give you the corollary that we observed, right? So let me rewrite. So what this tells me is that whenever the size of x is at least as large as size of f, I can construct an FD. So this, we have this implication. And if you take just the contrapositive of this, it says that if there does not exist a function that is not in f, in curly f, then it must be the case that the size of x is strictly less than the size of f. Right? Because whenever the size of x is at least the size of f, we can construct something outside of curly f. And so if you're in a situation that when we cannot do that, then the size of x is strictly less than the size of f. And when is a situation when we cannot construct a diagonal element? When do we have this? Well, when you have the set of all functions. Now, this is our notations. Let f of x be the set of all functions from x to 0, 1. If I'm considering the set of all functions, obviously I cannot construct f sub d, which is not part of f of x. This is the set of all functions. So in this situation, where I'm considering the set of all functions, which is this case, then it must be the case that the size of x is strictly less than the size of f. Okay, so the corollary of this is that for every set x, the size of x is strictly less than the size of f of x. Okay? Any questions here? And now we can, have a corollary to the corollary, right? So we can plug in different values with different sets for x and see what we get. So let's take the naturals, x equals the naturals. The corollary to the corollary is that the size of the naturals is strictly less than the size of f of n. The set of all functions from n to 0, 1. And this means, by definition, this means that f of n is uncountable. This is the definition of uncountability. And we can also plug in sigma star. So the size of sigma star is strictly less than the size of f of sigma star. So f of sigma star is uncountable. But what is f of sigma star? It's a set of all functions from sigma star to 0, 1. The set of all functions from sigma star to 0, 1, those are our good friends' decision problems. The set of all decision problems. So the set of all decision problems is this set is uncountable. And that now leads us to say the following, right? So we have the set of countable sets from last time. We saw that countability is really equivalent to encodability. These are encodable sets. And if you take any of these like infinite sets and apply the f operator on it and look at the functions, all 0, 1 valued functions on those sets, this is a higher level of infinity. These sets have strictly larger cardinality than these sets. And you could actually go further and apply f to those things and get a higher level of infinity and so on. So you have an infinite number or infinite levels of infinity if you want. You can just keep going like that. But for us, the important corollary of all this was the following, right? So this is the question that we started on Tuesday's lecture. Are there undecidable problems, decision problems? Right, so this is the set of decidable decision problems. This is the set of all decision problems. Is there something here or not? And now we're in a position, we have the mathematical tools to answer this question. Because as we just observed, right, so the set of all decision problems is just f of sigma star. And this, by a corollary of Cantor's theorem, is that this is an uncountable set. So we have uncountably many decision problems. On the other hand, if we look at decidable decision problems and ask, is the set of decidable decision problems countable or not? Again, to think about this intuitively, to understand this intuitively, you think about encodability. Countability is equivalent to encodability. Is a decidable decision problem encodable? And as we saw last time, yes. encoding of a decidable decision problem F, you can take it to be the encoding of a Turing machine that solves that decision problem. By definition, a decidable decision problem is one such that there exists some Turing machine that solves it. I can take an arbitrary, or there might be multiple Turing machines, that's fine. I'll take an arbitrary Turing machine that solves that decision problem F and use the encoding of that as my finite encoding of the decidable decision problem. So therefore, using the equivalence with encodability, we can say that this set is countable because it's encodable. And then we see that this picture is not to scale. Really, the set of decidable problems is a tiny drop in the vast ocean of, uncountably many decision problems. Like the difference between all decision problems and decidable decision problems, analogous to the difference between the set of reals and the set of natural numbers. Big difference. Okay, so this is the situation we have, and this means, this is just saying that there are just too many problems. There are just too many languages to handle. The set of Turing machines, a countable set, cannot handle all the uncountably many decision problems that we have. Okay? But here's an observation that you might have not thought about, but most of these decision problems, by the way, or most of these languages, cannot be even communicated among each other, right? So these are even beyond our, in some sense, mathematical analysis. If you take an arbitrary language which has arbitrary words in it, there is no way for me to actually define and communicate an arbitrary language like that to you. I cannot write it down with a finite description. Okay, it's just an infinite random-looking strings. So a lot of these languages we cannot even communicate among each other. So they don't, maybe you could say, even matter that much. So what's a fair game, or what's the more interesting question is, can I find a finitely describable language or a decision problem that is undecidable, right? So this is a problem that I want to be able to just write down on paper and say, look, here's the problem, here's the language, and this is undecidable. Right? That's what I want to be able to do. For example, the halting problem. Halting problem, the language, the halts language, it has a finite description. I mean, it has infinitely many words in it, but I can describe it to you mathematically. It has a finite description. And can I say now, okay, the halting problem is undecidable or not? Okay? So now this is a fair game, right? Because these two sets are countable. The set of finitely describable problems is countable. Decidable problems are uncountable. Now this is a fair fight. Okay, in some sense. And now I want to know, okay, can I find a finitely describable problem which is undecidable? In other words, another way to say this is that, so these can be mathematically communicated. Is there an explicit undecidable problem? Is the question. Is there an explicit undecidable problem? And what do you think now? We're going to answer this question. And what do you think we're going to use? What should we use based on what we've said so far? Yeah.
If we can create an injection between
diagonalize, yes, that's what I'm looking for. And we're going to do it, so don't get into the details. But I want to diagonalize against a set of all decidable decision problems and see what it spits out. Because as I told you, diagonalization gives you an explicit object, not in the set of objects you're considering, right? So if it gives me an explicit object, I'm going to use it. I'm going to try to use it if the setting allows me to do it. Okay, so this now brings us to limits of computation, the finite and undecidable. Okay, some language which I can describe to you in a finite way, but it's going to be undecidable. And the great idea that we're going to use is diagonalization produces an explicit object not in that set, and I'm going to try to use this. So let's come here. And there are various ways you can approach this, right? So you can directly diagonalize against a set of all decidable decision problems. You can try to diagonalize against a set of all semi-decidable decision problems. It turns out to be a bit more convenient to actually diagonalize against a set of all Turing machines rather than the decision problems directly. Okay, so this is what I'm going to do. Okay, so here's our picture for diagonalization in the general case. Okay, so this is diagonalizing against curly f. And now what I'm trying to do is I'm going to pick a particular curly f. My curly f is now the set of all Turing machines M. And I can do this because I can view a Turing machine as a mapping, right? It maps strings to 0, 1, or infinity. Why do I have 0, 1, infinity? Well, 0 for rejects, 1 for accepts, and infinity for looping forever. Okay, so there are three possibilities when you feed an input x to a Turing machine. Either it rejects, it accepts, or it loops forever. That's I'm going to denote by 0, 1, and infinity. So I can view every Turing machine as like a mapping, as a kind of like a function from sigma star to 0, 1, infinity. And I'm going to apply, I want to apply diagonalization. And what is the condition that I need to apply diagonalization? I need that the input space, in this case the input space is sigma star, is at least as large as curly f, which is the set of all Turing machines. Is this true? Is that condition satisfied? What's another way to say this? So there is an injection from curly f to sigma star. That means what? That yeah, exactly. That's the definition of encodability, right? So this is saying we need that the set of all Turing machines is encodable. Is the set of all Turing machines encodable? Yes, every Turing machine has a finite description. So this is a check. So then we're smiling, like we're like, oh wow, okay, now the condition of diagonalization is met, so we can diagonalize. Let's do it and let's see what problem comes out of it. Okay? All right, so now let me modify this picture, this general picture, so it fits our particular case here. Okay, so first of all, we know that the set of Turing machines is encodable, right? So there is an injection phi that maps M to some string. Let's call it x sum M. And here now, let's come here on this side of the diagram, on the table. I'm replacing the FIs by the Turing machines, M1, M2, M3, M4. This is the set of all Turing machines. I've listed them out. And then here are phi of M1, phi of M2, and so on. And now the table is a bit different. It's not just 0, 1, but you can also have infinity, right? So what this means is like M1 on the input phi of M1 rejects. It's a 0. M1 on the input phi of M2 goes to an infinite loop. So that's infinity. M1 on the input phi of M3 accepts. That's a 1, and so on. So you fill it out like this. And the way I'm defining f sub d here is so that, well, if it's a 0, if I see a 0, I'm going to make it a 1. If it's a 1, I'm going to make it a 0. And if it's an infinity, it doesn't matter if you make it 0 or 1, but I'm going to make it a 1 for this lecture, okay? So whenever I say an infinity, I make it a 1. Okay, so now I have a function from that maps these strings to 1 or 0. But okay, so now let's come to the condition here. The set of Turing machines is encodable. So let's make it explicit. What is this phi that we're going to use? What's this injection? It's the encoding function. Okay, so I'm going to take some encoding function for Turing machines. And I'm going to map M to the encoding of M. This is our notation for encoding, right? So now my table looks like this, M1, M2, M3, M4, and now I have the encodings of M1, M2, M3, and M4. Okay, so everyone's with me so far? Good. Suspense is building. What's going to come out of this? So let's put this up. Now, what's the conclusion here? So the way I've defined f sub d, right, is such that for every Turing machine mi, so this table contains all the Turing machines, for every Turing machine mi, the output of f sub d on the input, the encoding of mi, is different from mi and the encoding of mi, right? So if you look at this now, fd is different from m1, or the behavior of fd is different from the behavior of m1 because on input, the encoding of m1, they differ. This is 0, this is a 1. fd is different from m2 because on the encoding, on the input, which is the encoding of m2, this is a 1 and I made it a 0. fd is different from m3 with respect to the input, the encoding of m3. This is an infinity, this is a 1, and so on. So by construction, I've made FT such, I create FT such that it's different from each of these Turing machines' behavior. And so this FD, F sub D, which is now I can view as a decision problem, the output is always 1 or 0, is undecidable. There's no Turing machine. By construction, there's no Turing machine whose input-output behavior matches F sub D. Okay? You give me any Turing machine you want. You go home, you cook up some Turing machine, and you're like, this solves F sub D. And I say, no, it cannot solve F sub D because on the input, the description of your Turing machine, F sub D is different, the value, than what your Turing machine gives. By construction, that's how I construct F sub D. Any questions so far? Yeah, let's start here.
Are the descriptions of other Turing machines?
Yes, so here for everything else I'll put 0. It wouldn't matter. I could fill those in any way I wanted, and whatever F sub D I get is still undecidable. But for convenience, we're just going to imagine that everything else it's 0. Good question.
So, since we said that M is the set of all Turing machines, right?
Curly F, yes.
Yeah. So then wouldn't F sub D also be a Turing machine?
Which one?
The one we constructed, F sub D, wouldn't that also be a Turing
No,
machine?
so now I am constructing a function. So we're viewing these Turing machines as functions, mapping some input to output. So whenever I write M1, just think of it as like a mapping from sigma star to 0, infinity 1. And then I'm creating now another mapping, right, from sigma star to 0, 1, which differs from all the other Turing machines.
You could say it's a decision problem.
Yes, it's a decision, exactly, it's a decision problem, yes. Okay, so now let's see, what is this language? Let's look at the language that this corresponds to, the L. So when we have a decision problem, how do we figure out the language that the decision problem corresponds to? We look at all those inputs that map to 1. Those are the strings that are in the language, right? So what are the strings that map to 1? So let's look at so these are, we have 1s here. Why do I have 1s here? Right, so these 1s correspond to which inputs? They correspond to the encoding of M1, encoding of M3, encoding of M4. And why did I put a 1 here? Well, I put a 1 if it was a 0 here, and I put a 1 if it was an infinity. Right, so for all those strings, an encoding of, so this consists of encodings of Turing machines, M, such that what? Well, the encoding of the Turing machine is such that when I run that Turing machine on its own source code as input, it's either 0 or infinity. Right? So let me write that down. So it's this encoding of all those Turing machines such that when you run M on M, it's either 0 or infinity. This looks very similar to something else that you've seen. What is self-accepts? I mean, we had this in the poll. So that's the set of all those Turing machines such that M of M accepts, right? M of M accepts means that accepts. And how can I rewrite that? M of M accepts. M of M is 1. Right? Question? Yeah, it's basically the complement. It's like doesn't self-accept. Right? M on M either rejects or goes to an infinite loop. So in some sense, all those Turing machines, M's, that do not self-accept. It's the opposite of self-accepting. Okay, so what's the punchline here, right? So the punchline here is that when we apply diagonalization in the most straightforward way to, applying to diagonalize against Turing machines, it gives us naturally a language, a decision problem, which is undecidable. And the language that it spits out for us is the complement of self-accepts. Okay, so this is now the world's first explicit undecidable language, right? The complement of self-accepts is undecidable. And it just came out, I hope you see that it just came out of diagonalization. I didn't have to use any creativity to construct this language. Diagonalization spit it out for me, which is cool, right? So if you have a good understanding of diagonalization, how diagonalization works, if you're like Alan Turing and you're thinking about this, you just apply diagonalization and you're like, oh, this complement of self-accepts is undecidable. There you go. Okay, so now, that was the major part, one of the major parts here. Now, what I want to do is show that other problems are undecidable. What's another problem? From this, there's a direct corollary. What's another problem that's undecidable? Self-accepts itself, right? So if you tell me that the complement of self-accepts is undecidable, then I can tell you that self-accepts is undecidable as well. And why is that? Because if self-accepts were decidable, then I could use that to decide the complement of self-accepts. But we just showed that it's not decidable. Okay, so you can view it as a proof by contradiction if you want. So here's self-accepts one more time. M is a Turing machine such that M of M accepts. And the proof, go by contradiction. Assume for the sake of contradiction that self-accepts is decidable. And then, so there exists a decider, let's call it M sub SA, that decides self-accepts. And then using that M sub SA that we assume to exist, we'll construct a decider for the complement of self-accepts. Let's now denote that by M S sub A with a bar over it. And this is the way you describe it. This is a one-liner. You just do return not, right? So you just feed in the same input to this decider, M sub SA. Essentially, the reason why this works is because decidable languages are closed under complement operation, right? Because decidable languages are closed under complementation, this means that given that the complement of self-accepts is undecidable, it must be the case that self-accepts is undecidable, because if it was decidable, then the complement would also be decidable, but we know it's not. Okay, but yes, but self-accepts is undecidable, and that's the contradiction, and we're done. Okay, so now we have two languages in our pocket, undecidable. Well, let's keep going. What would be a natural next problem to consider when we want to show it's undecidable? What's a problem related to self-accepts? Yeah. Accepts, right? So in some sense, think about accepts. Accepts is like a more general problem. In accepts, you have to figure out, given some Turing machine M and some arbitrary input X, whether M of X accepts or not. In self-accepts, you're just looking at one particular input, which is the description of the Turing machine. So it seems like intuitively that accepts should also be undecidable. It's just like seems like a harder problem. And indeed, you can show this pretty easily, right? So accepts, again, is this problem. You're given input M, the description of a Turing machine M and input X, and you want to know if M of X accepts or not. And yeah, we're going to prove by contradiction. Again, the same principle. Assume for the sake of contradiction, accepts is decidable. So there exists, let's call a decider, let's call it M sub A, that decides accepts. And using this wonderful M sub A that I assume to exist, I'm going to decide now self-accepts. So I'm going to construct now a decider M sub SA deciding self-accepts. And yeah, this is how it looks like. This is also a one-liner. Who can tell me what the one-liner is? So I have a decider for accepts, which is M sub A.
Run M sub A, M, comma M.
Right, so return basically even m sub a, m comma, the description, m comma m basically. Right, and this will tell me, this wonderful machine that I assume takes this will tell me whether m on input, the description of m, whether that accepts or not, which is precisely what I want to know when I want to solve self-accepts. So now I hope everyone's happy with the general structure of this proof, right? So it's a proof by contradiction. Assume accepts is decidable. That allows me to now decide an undecidable language, and that's not possible. So this is a contradiction. Okay, so now we have three languages: complement of self-accepts, and accepts. These are all undecidable. Let's now do the famous halting problem. Halts is undecidable. And this is like, that was in the original, Alan Turing's paper. He showed halting problems undecidable. And now with everything we have, this is going to be relatively straightforward, I should say. Okay, so the halting problem is kind of similar to the accepts problem, right? So in accepts, I want to know whether m on x accepts or not. In the halting problem, I want to know whether m of x halts or not, whether it accepts or rejects. And what should I do? What's going to be the general proof strategy here, without giving the details? What's the proof strategy? Yep. Yep. A decider for an undecidable one, right? And what do you think? Which one should we use? Like, just intuitive. I mean, we have only three. I'm going to go with accepts. I mean, accepts and halts are pretty similar. So it's exactly how you said it, okay? So again, the same template. Assume for the sake of contradiction that halts is decidable. And then using this, so let's call this decider m sub h. And using this m sub h, I'm going to try to come up with a decider for an undecidable language. And in this case, I'm going to use accepts. So I'm going to now construct m sub a that decides accepts, and it's going to make use of m sub h. Now let's see how we can do this. Now, let's go back to the sort of naive idea of trying to decide accepts, which we observed does not work. The naive idea was you take m, you take the input x, and you want to simulate m on x and see whether it accepts or not, right? But this runs into a problem. Why? Because if m on x does not halt, then it keeps going and going and going. I don't know when to stop that simulation and give an answer. So m on x, if it does not halt, it creates a problem for me. But now I have this wonderful machine m sub h that I assume exists. It's a decider for halting problem. So if I now have this wonderful mh that decides halts for me, can I now solve accepts? How would I do it? What would be the strategy? Who can tell me? Yeah.
Could you run halts on the input Turing machine in the input, and if it returns true, you know it doesn't accept, so you return false. But if it returns false, you know that we can actually run the Turing machine on input, and it will return the answer in a finite amount of time.
Yeah, I think you swapped return true false, but yes, you're exactly right. Right. So the problem with the naive algorithm was that I cannot just simulate m on x because I don't know whether m on x halts or not. But now I have this wonderful halting decider halting machine. So the first thing I'm going to do is run, like feed into mh the input mx. Okay, so the first thing we're going to do is run mh on m and x to figure out, and this is assumed to be a decider m sub h. So it tells me in a finite amount of time whether m of x halts or not. And suppose it says no, it rejects. It doesn't halt. Then what should I do? Then we reject, of course, right? So if it rejects, if it says no, it doesn't halt, then it doesn't accept either, so we can reject. It doesn't accept. Else, what? Well, now, else it accepts. So the MH tells me that m on x halts. Well, if I know now that m of x halts, I am free to simulate it. I'll just simulate it now. I'm going to run m of x, see what happens. It either accepts or rejects. That's what MH tells me. So, and if it accepts, I'll accept. If it rejects, I'll reject. Okay, so that's the famous result that the halting problem is undecidable. Hopefully you agree that, all the pieces were falling down pretty naturally, right? So from diagonalization, applying diagonalization in a relatively, straightforward way, we got that complement of self-acceptance is undecidable, and through these connections, reductions, we got to the place where halts is undecidable. So then let's see some consequences of this. So what this tells us that, look, halting problem is hard, accept is hard. This means that program verification is hard, right? So what does that mean? So we write programs all the time, and we want to know whether our programs are doing what they're supposed to be doing, right? In particular, like I would like to know if my program has an infinite loop or not. That's like a very nasty bug to have. And one question is like, can I write a program that will tell me whether some other program has an infinite bug or not? Unfortunately, no. There's no algorithm that solves the halting problem, so there's no way to do program verification in general. And this is important because, software runs the world, right? And it runs our medical equipment, it runs our planes, flies our planes and stuff. So you want to be able to prove the correctness of programs. But unfortunately, there's no algorithm that will do this for us. One consequence of that is that there's no guaranteed auto-grader program, right? So when you're taking a programming course, the way auto-grading is done is like on sample inputs. They check the output of your code. That's just a heuristic. Like it doesn't guarantee that your code is correct on all inputs, but just on those sample inputs, it's correct. The reason we do it this way, auto-grading, is because, well, there's no algorithm in general that will do it. Consider the following program. I'm going to ask you, does this program halt or not? So what is this program trying to do? It's going through, it's a brute force search, it's going through n, x, y, and z. Is x to the n plus y to the n equals z to the n? And if it finds an x, y, z, and n such that x to the n plus y to n equals z to the n, it returns those values, right? What is this related to? Fermat's last theorem, right? And so it's trying to find a counterexample to Fermat's. Fermat's last theorem says that there exists no x, y, z, and n when n is like greater or equal to 3, such that this is satisfied. So imagine that I don't know how to prove Fermat's last theorem, but I write this program. It's a very easy program to write, and assume that I had a halting a program that solves the halting problem. Then I could feed this description of a Turing machine as input and figure out whether this Fermat's last theorem is true or false, right? So I could resolve, if I had a machine for the halting problem, I could resolve a major mathematical conjecture, or at the time it was a conjecture. Here's an excellent book on Fermat's last theorem if you want to read about it. It's a great book. Here's another one. This is written in Maple. This is the Canadian version of Mathematica. Okay, so we're very proud of this one. Which one? What mathematical conjecture is this related to? Does anyone know this one? Yeah? Oh, excellent. Yes, it is the Goldbach conjecture. So the Goldbach conjecture is that every even number is the sum of 2 primes. And this is a conjecture. We don't know how to prove it. But this is basically trying to find a counterexample to that. If it finds a counterexample, it will halt. If it doesn't find a counterexample, it runs forever. So whether this program halts or not would resolve Goldbach's conjecture, for example. And you can encode many other mathematical conjectures like this into a program, and whether the program halts or not will tell you what's going on. And the other thing is reductions show new problems are undecidable, and I'm going to say a few words about reductions in a second. So through reductions, we can show that Entscheidung's problem, Alan Turing showed the halting problem is undecidable, and then he reduced the halting problem to Entscheidung's problem to show that the Entscheidung's problem is undecidable. And that was the main question of David Hilbert, if you remember. Hilbert's 10th problem is undecidable. Again, you do this stuff through reductions. And yeah, then by physical Church-Turing thesis, once we show that a problem is undecidable, it is undecidable in this universe. Right? There's no mechanical process you can cook up in this universe using the laws of physics that we have to solve these kinds of problems. So it's really proving the computational limits of our universe when you prove limits of computation like this. Cool stuff. And let me actually, say a few more words about reductions and remind you the concept of a reduction, because in computer science, reductions is extremely important, right? It's like one of the key ideas, one of the great ideas, I guess, in theoretical computer science is the concept of reduction. And this is not going to be the last time we see reductions. They will come back again and again. They're very important. Now, in this context, like reductions can take different flavors. In this context, we are only interested in understanding the divide between decidable and undecidable. So we use it in that context. And we write A is less than or equal to B, where A and B are languages. If you can do the following, you can assume that there exists some decider MB that solves the language B. And then with that, you can now construct a decider M sub A solving A using MB, M sub B as a subroutine. So in picture, this is what we need to do. We want to come up with some Turing machine M sub A, right, that decides A. And we can make use of decider M sub B solving B as a subroutine. And in general, you can use it as many times as you want, this M sub B, call it more than once if you want, that's fine. Now, if you can do this, if you can actually show that A reduces to B, then notice that, of course, if B is decidable, then A is decidable. If B is decidable, this black box is now actually, we can replace it with an actual decider, and then the whole thing will be a decider for M sub A. Right? So when you're showing a reduction, of course, you don't care about M sub B. Showing a reduction from A to B does not require you to come up with a decider MB, not at all. You just assume it exists. You treat it as a black box. In fact, B may not even be decidable. Okay, that's also possible. So you don't care about that. You only need to make sure that you specify all the other parts correctly. And now what we are doing, or what we did with the examples, is that we use the contrapositive of this. Right? So we show that, well, this is equivalent to saying if A is undecidable, then B is undecidable. Right? So you can use reductions to expand the landscape of decidable languages, but you can also use reductions to expand the landscape of undecidable languages once you have one in your pocket already. Right? So in this sense, we think of A less than or equal to B as A is no harder than B. Right? So if B is an easy language in the sense that it's decidable, then this means A is also an easy language in the sense that it is decidable. And conversely, if A is a hard language in the sense that it is undecidable, then that means B is also hard, it is undecidable. Okay, so with respect to decidability, this is the less than or equal to sign makes sense, of course. And in terms of like programming, if you're imagining writing code, basically to give a reduction from A to B means you assume that there's some Python function that solves B for you. You don't care about the code inside. You don't know if it exists or not. But you just assume this exists as a helper function. And your task to reduce A to B is to actually come up with this piece of code. You have to write foo A for me that solves A. And you can call now foo B as many times as you want in foo A. Okay, so to show A less than or equal to B, give me the code for foo A. That's what you need to do. Okay. So so then this allows us to expand the landscape of undecidable languages. So if you show that accepts reduces to B, some language B, then B is going to be undecidable. Why? Because we showed accepts is undecidable. And we've shown like accepts reduces to halts, and this was our method for showing halts is, for example, undecidable. And then now if we argue for some other language B, Haltz reduces to B, then that would accomplish B is undecidable. That would show B is undecidable. And you can go on like this, right? One interesting observation here is that to show a negative result, that there is no algorithm, that something is undecidable, we're showing a positive result, that there is a reduction, and the reduction is actually an algorithm. Okay, so that's interesting observation, that we can show something negative by showing something positive, that there exists an algorithm. Of course, we have to start with something undecidable first. But yeah, just a small remark there. Okay, so now let's do one more example. Haltz, we're going to do now Haltz reduces to SAT. Okay, and since Haltz is undecidable, SAT is going to be undecidable, right? So reminder that these are the languages that we have. And yeah, so what is our task now? Let's think about this. This is the picture of a reduction, right? So since we want to reduce Haltz to SAT, we want to come up with a decider for Haltz. Let's call it M Haltz. That will use as a helper function an assumed decider for SAT. Call it MSAT. So this is the picture that we want to realize. We want to construct this thing. And here's my tip for you when you're thinking about reductions. Most of the times, the reductions have a very actually special restricted format. And it's actually very useful to restrict yourself to thinking in that format. So this is the way most reductions actually look like. Most reductions, you don't actually call MSAT like your helper function many times, but you call it just once. And in most reductions, whatever the answer you get from your helper function is the answer that you give in your reduction here. So if that's the case, then you really your task is to get the input, which is m comma x in the case of Haltz, transform it somehow, prepare an input that you will feed into your helper function MSAT. And then you want to make sure, of course, that in this case, if m of x Haltz, you want to prepare m prime in a way such that if m of x Haltz, m prime is satisfiable, so that this will give you accept. And if m of x does not halt loops forever, then m prime will be such that it is not satisfiable, so this will output false. So you need to make sure that this transformation is of that form. Right? I just want to emphasize one more time that this is a restricted form of a reduction, but most of the cases this works, and actually it helps you think about reduction. It narrows down your search space in some sense to when you're trying to figure out the reduction, and that narrowing down actually helps you. Okay, so you don't have to think about, oh, do I need to call MSAT like 5 times or 7 times? No, you just have to call it once and just make sure that you can transform this input to that input in the appropriate way. Right? So then your task is very clear. Okay, this is what I need to do, and then you think about how to do that. Okay, so let's try this out now. Okay, so I'm going to come to your ideas in a sec. But this is what we want to do, right? We want to define the m Haltz, takes an input m and x. And what do I need to do? I need to prepare m prime. I need to prepare the description, a string representation of another Turing machine m prime. So this we can represent it like this. So it's like defining a new string within m Haltz. Let's call it m prime. And then once I define this, of course I have to define what this is, but after I define it, what am I going to do? I'm just going to return MSAT m prime, right? Because this is the picture we have, right? We're going to just directly feed m prime into MSAT, and that's supposed to give me the right answer. So now the whole, thing here is, well, how do I define this m prime? And I think, yeah, I already heard some good ideas here. But let's do it together, okay? So let's do it together slowly. So notice that the task is given m and x, I need to create this m prime. So m prime, of course, is going to have m and x inside it. It's going to depend on m and x in some way. It has to, of course. Because somehow whether m prime is satisfiable or not should tell me whether m of x halts or not. So I have to create that situation. So these are the two possibilities that I need to distinguish. M of x halts or m of x loops. I need to make a distinction. I need to figure out how I can make that distinction. And how is this going to play out with respect to m prime? Well, if m of x halts, I want m prime to be satisfiable, right? So that the language of m prime is not the empty string. That's what it means to be satisfiable. And if m of x loops, then I want L of m prime to be the empty set. It's not satisfiable. There's no string that makes m prime accept. So I need to make these correspondence. So now, given this, let's think about this, right? So how can I write the code for m prime such that these implications are satisfied? And maybe now I'll come back to you. I think your answer was?
Yeah, you can make, I guess, you can make m prime accept x if m of x is like either 0 or 1 and then reject it.
Okay, so I hear some good ideas there, for sure. You want to you want to do something with m and x, right? So what can I do with m and x? Yes?
Why can't you just run m on x, and then after just accept?
Very good. So let's run m of x, okay? So what does this, and then accept, as you just said, right? Okay, so now let's see what's going on here. So again, let's see if the conditions are satisfied. If m of x halts, right, what's happening? Well, I run m of x. I completely ignore what the output is. I don't care about what the output of m of x is. I go then, if it halts, I go to the next line and I accept. Right, so then it means that for any y, input y, I will, if it's the case that m of x halts, I will accept. Okay, so in this case, actually, let me write this down. In this case, m of x halts means actually that L of m prime is sigma star. It accepts everything. And definitely, if it's sigma star, it's not equal to the empty set. Right? If m of x halts, it will accept every string, every y. And then it, oops. Oh, okay. Oh, man, slow animations. Okay, so we had this. And what if it loops? What if m of x loops? What happens? Well, then, you come here and you're stuck. You're running m of x. This is just looping forever. It just goes. So what does that mean? You're just stuck there. You never make it to the next line and accept. So if you're always stuck on line 1, do you accept any string? No, you're just stuck. You can never accept any string. So then, indeed, the language of m prime is the empty set. Yes?
Why don't we use y?
Why don't we use y? Because, yeah, we don't need to. Because, right, we've accomplished this implication. It didn't require us to actually even look at y. Because no matter what y is, we're just doing the same thing. Right? So if m of x halts, then I'm always going to accept no matter what y is. So that leads to L of m prime being sigma star. And if m of x loops forever, then for every y, I'm just stuck on that loop, and it never accepts any string.
Where's the m prime that's returned being produced in this function?
The m prime is this. So let me make this comment here. What m halts is doing is merely creating the string representation of m prime. It's not running m prime. It's not running m of x, therefore. It's just creating the string. Like imagine like in Python you write this function, right? So you're just like creating the string. And this is why it's actually a decider, right? Because mHaltz, all it's doing is create the string m prime, as you see here, and then return mset. Creating a string is, of course, you can do that. There's no problem with creating a string. Right? And then calling mset, well, since this is a decider, mset is assumed to be a decider, this whole thing is going to be a decider. In particular, of course, mHaltz is not running m of x. If it was running m of x, then it would not be a decider. We're not running m of x here. We're just creating this string, the encoding of some other Turing machine m prime that we use as input to mset. Okay? Okay, so let me now, I'll leave this as an exercise, sat to not equal, which is a good exercise to do, right? So this is now, we're going to reduce sat to not equal, and this will accomplish now that not equal is also undecidable. Great exercise to test your understanding, okay? Let me very quickly show you some other examples of undecidable languages that don't involve descriptions of Turing machines or descriptions of other things. So Entscheidung's problem we already talked about. This is what Turing proved in his original paper. Hilbert's tenth problem is undecidable, right? This is also we discussed. Let me give you like maybe this one. This is like post-correspondence problem. You're given a collection of dominoes, okay? And it has like, upper half and lower half, which each contain a string. And you want to know, can I actually put these dominoes together? You can use as many copies as you want, in a way such that the top string and the bottom string match, like this. This is undecidable. Here's another one that I like. This one is like two 21 by 21 matrices you're given as input. And you want to know, can I like multiply these matrices U, V? You can use as many copies and U and V as you want, in a way such that you get to the zero matrix. It's undecidable from 2007.